science time, we're going to talk about electricity, or sorry, let's phrase it this way, like your book does. Electric forces. Electric forces. Okay? So you can see there's this picture in your book, right? Of, well, what you describe it. I want to hear it. Raise your hand if you can describe this picture. Do you think? Peyton, what do you think?
It looks like electricity going through these magnetic balls.
Okay, so let's continue describing. Peyton, you were describing what this picture looks like. Let's all listen to Peyton, please.
It looks like electric moving through these metal balls.
Right, so there's these two,
Passing it through each other.
right, there's two metal towers here, right, that have balls on the top of them, and there's some kind of electrical, well, we see there's electricity. How do we tell that there's electricity there? This is what we call electricity. This looks like what? A lightning bolt. It looks like a lightning bolt. Yeah, Justice.
I was going to say they're Tesla coils.
Yeah, they are Tesla coils. That's exactly what they are. They are Tesla coils. So it says below it, Jaden, would you read what it says below it, please?
Electricity takes many forms. An electric arc and lamp lighting up when it's plugged in or are both caused by the same basic property of magnetism.
Right, so this electrical arc from this Tesla coil is caused by the same thing that causes the light bulb to light up. And you know that, right? You've heard of electricity, you know what electricity in general is. Okay, so I want to show you this thing. Okay, so in that little video, which you can, if you're not here, or if you are watching the video, you can watch this video that we watched by typing in, I'm sure, water droplet knitting needle ISS, right? ISS here stands for the International Space Station, right? And so what happens is there's the knitting needle and the little water droplets are, it looks like, orbiting around it, right? And so why in your estimation, based on what we've learned before in the class, why do you think it's important that it happens on the International Space Station and not here? Why can't we just do this in the classroom? Why can't I just show you this in real life, or right now, right?
Because we're not the gravity.
Right, because gravity, the forces, remember we talked already this year about forces, but here in the classroom if we were to try that, the force of gravity would be much stronger than the electrical force that's allowing those droplets to orbit the knitting needle. So if we tried that here, the droplet would just fall down due to gravity, right? Okay. So let's think about let's brainstorm some ideas that we already know about the electrical force. First of all, using the knitting needle demonstration as a guide, why do you think, what force is being applied to those water droplets as they go around the knitting needle?
Gravity.
Nope, not in that case, but that's why we just said it has to be on the ISS.
Gravity where they're-
There is gravity, but what's happening is the whole space station is falling, and so it's as if the gravity doesn't exist, right? It's all in free fall. Anyway, so gravity is not the force acting on those droplets to make them go around the knitting needle. What do you think is?
Stuff.
The electric force. The electric force, right? Which we actually call this force, the word we generally use in science for this is the electromagnetic force, right? So when we're talking about electric forces, the word we use in science is called the electromagnetic force, which obviously is a combination of two things, right? Magnetism that we learned about in the last lesson, and electricity that we're going to learn about in this lesson, right? And so just like magnetism, electricity, was that, how would you describe the interaction between that knitting needle and the water droplet? They were what to each other?
Repelling or...
Yeah, well, so to some extent they were repelling because they weren't, it's not like the knitting needle was here and the water droplet was just, right, just didn't go right straight to it. So there was something, it was somewhat repelled, right? It wasn't going right toward it, and it was somewhat what?
Gravitating.
It was somewhat attracted, right? Let's not use the word gravitate because that implies that's because of gravity. So we're going to say electromagnetic forces can be, just like in magnetism, what or what? What two adjectives? They can be what kind of forces? Whereas gravity only draws things together, right? Both electricity and magnetism can be what words? Yeah? Yeah, so we can say that they are attractive and repulsive, right? If you ever hear this word in your normal life, what does it probably mean?
Looking at someone's face.
No.
Always, Peyton? No.
Like, not attracted to.
Right, yeah, so
Not
it's
attractive.
basically it's the opposite of this, right? So in Peyton's awful example, right? If you find someone else's face repulsive, which you should never tell them because you should be a decent person, but what that means is that it repels you as opposed to attracting you, right? So this means for things to draw together, and this thing means for them to fall, or to not fall, but to push apart, right? And so, just like magnetism, how was magnetism attractive and repulsive? You remember? Like, in what way, what could we do with magnets to show that they are both attractive and repulsive? What do you think, Peyton?
You can put two light poles toward each other, and so they'll, like, I don't know how to
They'll repel.
They repel,
They'll
right?
repel, so they'll push away, and then when you put two opposites towards each other, two opposite poles together, they attract.
Perfect, exactly, just so. So, in magnetism, when we had two like poles, they repel, and when we had two opposite poles, they attract. And it's the same way with electricity. So we can write this. In electricity, oops, I spelled it wrong. It's the same thing. This is one of the most important things in all science. It's almost like a cross-cutting concept that we have in there, right? It's almost that magnitude of importance because in electricity, opposite charges do what?
Attract.
Yes. Opposite charges attract, and like charges, fill in the blank.
Poles.
We say repel.
Repel.
They repel one another. And this is so important because it's not just about all the demonstrations we will do in this lesson, like when you guys do your lab, that'll be all about what we call macro scale objects, objects you can see and feel and touch. But this little principle here, the principle of electrical attraction and repulsion, is what holds you together as a human being, right? The particles that make you up, which are called atoms, right? The particles that make you up are made of, you know what three things atoms are made out of?
Neutrons, protons, and electrons.
Yep, neutrons, protons, and electrons. And those things have electrical charges. And then the attraction between those things is what holds you as a person together. It's what causes chemical reactions to occur, right? This is basically, this sentence here is the fundamental nature of chemistry. This is what makes chemistry work. And you are basically a very complicated pile of chemistry. So everything in the universe, to some extent or other, relies on this principle. In fact, we call it, this force, the electromagnetic force, is one of the four fundamental forces of the universe. Do you remember talking about this? Or did we already? Can you guess what one other fundamental force might be? Just guess. Gravity. Gravity is one of them. There are four fundamental forces of the universe. We'll talk about this later on, maybe even next year. But they're the electromagnetic force, which we're talking about now, gravity, which we talked about in the last unit, and there's two others called the strong force and the weak force that are a little more mysterious. We don't have much physical, like we don't deal with them, we don't think about them on a daily basis because they don't have macro scale implications usually. But we will talk about them when we get to physical science. Anyway, for now, you should know that the electromagnetic force is one of what we call the fundamental forces of the universe. So as opposed to the magnetic force, though, with electrical charges, we use this notation. Electrical charges can be positive or negative. So instead of north and south poles like we have with magnets, we use positive and negative. And this notation makes it easier to work with the numbers when there are numbers. Speaking back of atoms, protons, neutrons, and electrons, Sedona reminded us. Which of those has a positive charge? Do you know? If you don't know, don't just guess, but do you know which one of those has a positive charge? Protons have a positive charge. Which one had a negative charge? Be careful because people get this wrong.
Neutrons.
Nope.
Electrons.
Electrons have a negative charge, and neutrons are neutral. And so that's another thing that we talk about with electrical charges. Electrical charges are always either positive or negative. But when we're talking about electrical charges, some things can also be neutral, meaning they have no charge. So let's put this. Neutral is what we call it when it has no charge. Usually, just give me a second, please. Usually, it doesn't have no charge because it doesn't have charged particles. Usually it has no charge because they balance out. In the same way, do you remember when we were talking about forces?
Nope.
We said there was either a net force or there was no net force, right? And when it was no net force, did that mean there were no forces acting on it?
No.
No, not necessarily. It could also mean that the forces did what? balance out. Yeah, the forces all add up to 0. So in the same way, usually when an object is neutrally charged, it's not because it has no charge at all. It's because the charges balance out, right? So like you're made out of protons and electrons, we already said, right? You, at this moment, probably don't have a very large electrical charge, even though you're made of hundreds of quadrillions of protons and electrons, all of which have a charge, right? But they balance each other out. You have just almost exactly as many protons in you as you do electrons. So you have no net charge. Does that kind of make sense?
What if you don't?
Well, we're going to talk about it in a second.
So are neutrons just meant to take up space?
That's not, I don't know, we don't really say things like purpose, but that's not what they do in that. We will talk about it when we talk about matter. But no, they have another job. We don't really use that word, but they have another role that they play in the atom. Anyway, so generally, here's a picture. I'm going to try to replicate this picture. Generally, if an object gains a negative charge, what will its charge be? This should be pretty, yeah, it'll be negative. It'll have a net negative charge. If it loses a negative charge, what will its charge be? Positive. It'll have a net positive charge. And the reason we say gain negative or lose negative is because generally it's the electrons, the negative particles, that are being transferred. Generally, I'm just going to write that up here as a little side bit. Generally, electrons, which are negative, are being transferred. Right? And so because of that, since the electrons have a negative charge, we generally say something has either lost a negative charge or has gained a negative charge. Generally, things don't gain a positive charge. That doesn't mean things can't be positive, right? How would something become positive? By losing electrons, right? By losing electrons. How would something become negative?
By getting more.
By gaining electrons. The positive charges, the protons don't usually normally transfer, at least not in large enough quantities to make a difference. So I'm going to try to draw this little thing over here. So if we're going to start with two objects, this will be the point of one of your labs. Here we have balloon. Can you tell that I drew a balloon?
Yeah.
Okay, who wants to be me to draw them? Okay, I'm going to draw Peyton. Oh wait, he's got a mask on.
Oh yeah.
Perfect. Okay. Anyway, so when they start out, they both have what kind of charge? Just in normal life, things that we normally encounter have what kind of charge?
Said I had a normal.
Yeah, neutral.
They're normally neutral, right? And once again, is it neutral because it's not made of charged particles?
No.
It's neutral because they balance out. So we're going to draw just as many positives as negatives, right? Kind of like your life, right? Your life is not all positive and it's not all negative. There's a balance of both. Anyway, in the same way, Peyton,
Mr. Krabs.
Eugene Krabs, is made of charges that are both positive and negative, right? So right now they're both say the word, neutral. Right now they're both neutral. And you've done this before, but in step 2, when we do this,
You rub it against over.
when we rub it against his little head, what happens is some of the electrons, the negative charged electrons from Peyton's face or head or hair or whatever, transfer to this. So now this has a more negative charge. It still has the positive charges it had before, and it still had the negative charges it had before. But now it took some electrons from Peyton's head, and so now he has what?
Dumbest, you know.
That's positive. Right?
Yeah, listen to what Justice says instead of talking to each other.
More positive.
Right, because he has lost some electrons, he has now a more positive charge, right? He still has some electrons.
So technically.
But listen to me, please. He still has, now because he has lost some electrons, he has a net positive charge, right?
Actually, like,
And because the balloon has gained some electrons, it has a net negative charge. And what do we know about opposite charges? They attract. And so the balloon is going to be stuck to Peyton's head even when we don't touch it. Yeah, so we're going to do that in one of your labs tomorrow. Yes?
So technically you're saying that, like, the balloon, like, stole his negative charge.
Yeah, yep. You can't see it.
He got down.
Yeah, so the electrons were moved from him to the balloon. What else? What do you sometimes do after you've probably done this? After you rub the balloon on your head, what do you sometimes do with it? Stick it to the wall or the ceiling, right? And so I think this is the coolest thing. This is something called, we're going to draw step 3 here. This is something called electromagnetic induction. So the wall starts out with a neutral charge. I'm not going to draw that, but the wall starts out with a neutral charge, right? Right?
Right.
Right now the wall is just neutrally charged. What happens is when I bring the balloon that now has a what charge?
Negative.
Right, it now has a negative charge, a mostly negative charge, right? It has more electrons than it did before. The wall, which was neutral, it's going to stay mostly the same, except now, because it has this net negative charge, the wall is also, since it's neutrally charged, right?
Why did it have
The positives, which are more attracted to the negative balloon, look. But also, since this is mostly negative, right?
Yeah.
Well, how do these little babies, how do the electrons that are in this respond?
Like, no, get away!
Just think, if you're just an electron, what's going to happen to you when this big negative thing comes over to you?
You're gonna repel.
Yeah, it's going to repel. So basically the electrons all scooch out of the way. They move further back into the wall, just like a tiny bit. But they move further back in the wall. So now the charge that's mostly showing on the wall is what?
Positive.
Which makes it do what with this?
Attract.
Attract. So that's why when you rub the balloon on your head, electrons go from your head to the balloon, making it negative. And then when you draw it near the wall, the electrons that are already in the wall are like, nah, dog, I'm out of here. And so they leave a little bit, which makes this mostly positive, even though this never lost any charge, right? Right? Unlike you, Peyton, unlike you getting it rubbed on your head where you actually did lose the electrons, the wall hasn't lost anything. It's just that they move out of the way, and so now it's attracted to the wall too. And this whole broad category of electromagnetism is called, can you guess? What kind of electricity? Static electricity. This whole thing is called static electricity, as opposed to, and we'll talk about this later on in, I think not the next lesson, but the lesson after the next lesson. Static electricity is opposed to current electricity. So like when the electricity running my webcam right now, and the electricity running your laptop, and the electricity that powers your phone is something called current electricity, where the electricity is flowing from one place to another. In static electricity, the charges exist on objects, right? Instead of actually moving around, the charges stay in place. They are static. They stay in place. Stay, the word stay, has the same root word as static. They mean the same thing. The charges are staying in place. One last thing before we finish. Where have you heard of static? Like if your mom or dad ever told you about static electricity, it was probably when what happened? Yeah, right, exactly. When you shuffle your little socky feet across the carpet and shock your brother or whatever, right? And that's what's happening there. Listen to me. I'm going to explain that in a second. Okay, I was going to draw it, but I kind of ran out of room. But what's happening? Well, you tell me what's happening. When you shuffle your feet across the floor, what's probably happening in this picture?
The floor's negative charge is moving to your feet.
Exactly. Your feet are building up a negative charge from the floor, right? You're taking some electrons from the floor, okay? So far, so good. So what's your total electrical charge now?
Negative.
Negative. And that spreads kind of throughout your body, right? The electrons move very quickly and they kind of cover your whole body. And then as you're shuffling, you go up to your brother who has what kind of charge?
Positive. Wait, no.
Let's all agree on it. What is it? He's just sitting there on the couch. What's his charge?
Positive.
Neutral.
Well, let's all agree. Let's all agree. Neutral, right? He has things in general when they're just existing have a balance of positive. So you have built up a negative charge. You're going to go over to him who has a neutral charge, and unlike this, because the balloon was so dang light, it could just be attracted to the wall. That's not going to, your finger's not going to be like whoop, and you're going to like be attracted to him, right? But what's going to happen is the electrons your whole body has built up, which is making you non-neutral, are going to move from you to him. It's going to spread out. The charge is going to what we call disperse. And that shows up as a, what? What does that look like when you touch it? Yeah, a little, right? A tiny little, exactly what Rhett just said. Say it again, Rhett. It is literally the exact same thing as lightning. The only difference is when it's you shuffling across the floor and touching your brother, it's smaller than what do you think is happening when there's lightning in the sky? What two things are rubbing?
It's rubbing against the clouds.
Basically, yeah, the cloud is just rubbing against the ground. That's all it is. It's shuffling and building up electrical charge from the ground, and then in one little place, all that electrical charge that built up from the ground blasts onto a church steeple or a tree or a golf club or a cow or something, right? You know what I mean? Hey, listen. I phrased it kind of funny, but you understand what I mean? It is the exact same thing, because all it's doing in both cases is some object, because it's moving across another object, is building up a negative charge, and then when that charge is dispersed, it shows up as a lightning bolt. Just like the thing at the front of the Tesla coil at the front of our chapter, right? Do you have questions about this? I don't know if that's true or not, but you will get questions as you do your exploration. But does this seem like it makes sense to you? Does this kind of explain something that you've had in your life for a while?
Yeah.
Okay.
Sorta, kinda.
Okay, bye.
Bye bye.